All right, friends, here we go with another question. This is the 2015 BC International Exam, question number 3. Here we go. Oh, and this, because it's question number 3, no calculator. Kathleen skates on a straight track. She starts from rest at the starting line at time t equals 0. For 0 less than t less than or equal to 12 seconds, Kathleen's velocity k, measured in feet per second, is differentiable and increasing. Whenever I come across these important adjectives, I'm gonna underline those, remember those for later. Values of k of t at various times t are given in the table above. In part A, we're asked to use the data in the table to estimate Kathleen's acceleration at time t equals 4 seconds, show the computations that lead to your answer, and indicate units of measure. Okay? A pretty standard question. K of t is velocity. I just want to make sure that we're all super clear on this. This is a velocity function. So how do I find Kathleen's acceleration, a of t? Well, we're going to find the derivative of her velocity. The problem is we don't have the velocity function. We don't have an equation, so we can't go and just take a derivative using like product rule, quotient rule, chain rule. That's why they ask us to approximate her acceleration at 4. Well, her acceleration at 4 is the same as the derivative of her velocity. But as we've seen before, derivative means slope of tangent. And unless I have the equation, I can't come up with the exact value. However, what I can do is I can say the slope of the tangent line is approximately what I get if I look at the slope of a secant line. The difference between slope of tangent and slope of secant, I need 2 points. And this is why we go to the data table. We're going to look for points that are as close to t equals 4 as we can. And you're going to, so 3 and 5, we're going to find the velocity at time 5 minus the velocity at time 3 divided by 5 minus 3. This is the slope of the secant line to approximate the slope of the tangent. I can see from the table velocity at time 5 is 10, velocity at time 3 is 5, divided by 5 minus 3, simplify if you want to 5 over 2. What are the units? Well, your velocity is feet per second. The time is in seconds. So this is feet per second, or feet per second squared. They awarded 1 point for the approximation and 1 point for the units for a grand total of 2 points. Now, I just noticed I was a little sloppy here, and I want to make sure that we bring attention to this. I said acceleration is the derivative of velocity. That's true, but I don't actually have a function named v of t for velocity. It's k of t, and this is one of those really lethal mistakes. Don't use v prime, make sure this is a k. All these v's are k. K of 5 minus k of 3 divided by 5 minus 3. That may or may not cost you a point on the BC exam, but let's make sure, especially in this video, that we're setting those expectations really high. All right, that's it for part A. Let's look at part B. In part B, we're told to use a right Riemann sum with the 4 subintervals indicated by the data in the table to approximate the value of the integral from 0 to 12 k of t dt. Integrate 0 to 12 k of t dt. Indicate the units of measure and then determine if the approximation is an overestimate or an underestimate for the value of the integral from 0 to 12 k of t dt. Whew, we got a lot going on here. Well, what do I know? I know that we are supposed to use the right Riemann sum with the 4 subintervals used above. Now, I want to be careful because often students will say, oh, we're going to go from 0 to 12, we need 4 rectangles, each rectangle has a width of 3. We don't have that information. We have specific points on the journey that we can use. So if I do a little like number line over here, we've got 0, 3, 5, 8, and 12. We're using the right endpoint method, so for each of these intervals, we're going to take the width of that interval, so in this case 3, times the value of the function at the right endpoint. Well, the value of the function at 3 is 5, plus your next interval. How wide is it? 2. What's the height at time t equals 5? 10. Plus your next interval. How wide is it? 3. Times the velocity at time 8. That's going to be 20. Plus your last interval. How wide? 4. Times the height. Velocity at time 12 is 24. And if you multiply all of that out, that's going to be 191 feet. Since this is the calculator inactive part of the test, I would not, under any reason, multiply all this out and get 191. There's no need to. Okay, now you might think we're done, but we got to keep going. Units of measure, well, K of t was feet per second. So feet per second. dt is seconds. The seconds cancel out and we get feet. Okay, I already did that, sure. Then we've got to determine if our approximation is an overestimate or an underestimate for the value of the integral from 0 to 12 k of t dt. And a popular thing that students are going to do, let me use a different color marker here. They're going to think about the graph. They're going to say, here's 0, 0. Here's 3, 5. Here's 5, 10. Here's 8, 20. Here's 12, 24. And they're going to say, I can see from the graph that those points are increasing. Here's the problem. Just because the function seems to be increasing at these 5 points, that's not good enough. You're going to have to explain to me what's happening to the function on this interval 0 to 12. Well, what do we know? We know that for the time interval 0 less than or equal to t less than or equal to 12, k of t is increasing. That doesn't come from the graph. That comes from the initial word problem. They told us that the graph was increasing. Okay, well, why do we care about that? Well, think about what we just did. We made our rectangles using the right endpoint method. That means that for each interval, you go up to the curve, over and down. Up to the curve, over, down. Up to the curve, over, down. Up to the curve, over, down. Your curve is supposed to be increasing, and so each of these rectangles contains more area than it's supposed to be. Now, don't just say the rectangles contain more area. I'd say for 0 less than or equal to 12, less than or equal to 0 less than or equal to t, less than or equal to 12, k of t is increasing, and we are using the right endpoint method, which I'm going to abbreviate as REM. Therefore, the approximation is an overestimate. Whenever you're doing problems like this, your justification has to involve two things. You have to tell me what the function is doing, and you need to tell me about the method being used. Putting those two things together gets us what we need. So in terms of awarding points, the setup here gave you the first point. The numerical value with units got you the second point. And then being able to say that there's an overestimate and justifying with mention of the behavior of the function and the approximation method being used, that gets you your 3 points. Hopefully you did well on this question. Let's keep going. Sorry about that. We had a little bit of a technical difficulty here. So let's look at part C. In part C, we're told that Nathan, apparently we're done with Kathleen, skates on the same track, starting 5 feet ahead of Kathleen at time t equals 0. Nathan's velocity in feet per second is given by this expression over here. Write, but do not evaluate, an expression involving an integral. So we're going to have something involving an integral. that gives Nathan's distance from the starting line at time t equals 12? Well, let's think about this. At time t equals 12, what's going on? We know that he's already 5 feet ahead of Kathleen, and now we've got to consider his velocity. We know n of t represents his velocity, but this is a location. I know that if I integrate the velocity from 0 to 12 of n of t dt, what this is going to do is this will give me his displacement from t equals 0 to t equals 12. Displacement, of course, is change in position. From t equals 0 to t equals 12, this is his change in position. The 5 is his initial position. And so what we're going to get is his final location at t equals 12, or his final his distance from the starting line. College Board offered 2 points for this. There was 1 point for the integral expression. There was 1 point for the whole thing, meaning you remember to include the initial position, for a grand total of 2 points. Not too bad. Let's look at part D. In part D, we're asked to write an expression for Nathan's acceleration. Well, we've already seen this before. So acceleration, we know, is the derivative of velocity. Well, we need the derivative of Nathan's velocity. Well, how do we find that? N prime of t. I see n is 150 over t plus 3. Minus 50 e to the negative t. That's looking a little bit blurry and I'm not sure why. Sorry about that. Okay, that's better. To find the derivative of 150 divided by t plus 3, we're going to use the quotient rule. So low d high, derivative of 150 is 0, minus high d low, all over low, minus the derivative of 50 e to the negative t. Well, that's 50 e to the negative t times negative 1. That times negative 1 is coming from the chain rule. And all they've asked me to do is come up with an expression for his acceleration. Here we go. They didn't ask me to simplify. However, if you do want to simplify, let's simplify correctly here. T plus 3 times 0 is 0. So in the numerator we have negative 150. We have t plus 3 squared. Minus 50 e to the negative t times negative 1 is the same as plus 50 e to the negative t. College Board awarded 2 points for this answer. And when they do something like that, it tends to be an all or nothing thing, meaning that if you, I don't know, for example, did the quotient rule correctly, but blew it over here on the chain rule, they are likely to award 0 points here. So you want to be really careful. But that's it. That was question number 3. Not too bad for a Calculus BC exam question. I would expect this to be a really high-scoring question without too many places where we're going to get turned around.